delay. We already started the exercises a bit delayed, and now we carried it over to the lecture. Nevertheless, welcome to today's lecture on symmetric modes of operation. So we're essentially done with looking at the symmetric primitives now, and now we want to look at how we can compose them into schemes on a higher layer of our crypto stack. And we're going to have 2 lectures in total on modes of operation. Namely, today we will first focus on authentication modes, and afterwards we want to have a look at encryption modes next week. Yeah, so this is a bit of a switch from last week. It appears that people don't hear anything except noise. Okay. Sorry, YouTube people, I hope you hear the right stuff, but this needs to be quickly fixed on Teams. So hi again, at least the people on the Teams stream. I hope the sound is working better now. Let me just share my screen again. Excellent, thanks for confirming. Let's have a look at the slides. Okay, there we go. So what I was saying already before the sound was working is to try to give a bit of an overview of where we currently are in the lecture. So I was explaining that in the last lectures so far, so lecture 2 to 4, we were mostly talking about symmetric primitives and looking inside of them. Whereas this week and next week, we want to talk about modes of operation, so moving up further in the stack. And the plan is that today we want to look at modes for authentication, so for confirming the origin and the integrity of messages, in particular looking at hash functions and MACs. And next week we want to look at modes for confidentiality, so for encryption and authenticated encryption. If you already listened to the information security lectures, you will already recognize some of the modes that we look at today. But I promise there will also be some new things. If you haven't heard information security yet because you just joined for the masters or you are from a different curriculum, I will try my best to recall a bit what these functions are intended for and what the main ideas for building them are. Okay, so let's have a look in more detail at what the plan is. I first want to have a few words about the general goals that we have in cryptographic authentication and what sort of applications this is used for. And then we want to discuss hash functions, which are unkeyed functions providing authenticity. And we will have a look at the definitions of when a hash function is considered secure. We will see some generic attacks on hash functions in general, but also on the specific constructions that we look at, which today includes the Merkle-Darmstadt construction and sponges. And we will have a look at some of the analysis techniques that determine how secure these functions can be. And afterwards, in the second half, we want to have a look at message authentication codes, which are a keyed version of authentication, but symmetrically keyed. So both participants need a shared secret key in order to use the message authentication codes. And again, we want to discuss both how they are intended to work, so what their defined interface and their security properties are, and second, how to build them. So let's have a first a look at authentication in general. Authentication actually means two different things in cryptography. The first meaning that we want to be dealing mostly with today is the meaning of message authentication. Meaning we want to, when we have a communication channel, we want to provide authenticity as well as integrity. Where authenticity means that we can verify the source of a message. So who sent it? Was it the other owner of the shared secret key, or was it somebody else? And second, integrity. So we want to make sure that the message was not modified in transit. There is also a second meaning which we will take on again a bit later, namely the meaning of entity authentication. This is now not tied to a specific message, but in entity authentication we want to make sure that we are currently talking to a particular user or device, where that user is identified by possession of some key or password. So the first thing is related to messages, and the second thing is related to who are we talking to right now in this moment. And there are now different schemes, all of which create some form of message authentication, but we have at least 3 different types depending on what sort of key infrastructure we use. So first we have the unkeyed case, where anyone can compute the tag for the message, so the piece of information that is supposed to certify the authenticity, and also anyone can verify it. So both is possible for everyone without possession of any key. We also have 2 keyed versions. First one where both people share the same secret key and both of them can compute and verify tags. This is the symmetric case we talk about today. And then there's the asymmetric case where only one person can compute the tag, but everybody can verify it. And these are the different scenarios that we're interested in. Now, each of these has specific applications where it's more suitable. So for example, a hash function is suitable whenever you don't only have the one communication channel you're talking over, but you have a second secure channel where you can transmit smaller pieces of information. For example, the large piece of data you want to transmit is something like a Linux image or your LaTeX distribution, some big piece of software, which you can't directly host on your server, but for example, you distribute it in a peer-to-peer network. And then you have a second secure channel where you can't transmit as much, such as, for example, your home page. So your website where you can host something like a hash value of the distribution image, but you can't host the entire thing. And people then can pull the big thing from the external untrusted source, like a peer-to-peer network, and then recompute the hash of the thing and compare it with what's written on the website to be sure that it's the correct file. Being the correct file is also a general application of hash functions, even without a security context. So hash functions are often simply used to identify a file in a file system, for example, in cloud storage, or to identify when there are multiple files with the same content. This is done not by comparing every file byte by byte with every other one, but by storing a hash of each file and then looking for collisions, which in this case imply that the input file is also the same. You can also find it as an ID, for example, when you look at your Git and you check out a particular Git commit. You also do that by specifying its hash fingerprint. The max scenario is useful whenever you already have a working infrastructure. A working infrastructure could, for example, be that you already have set up a communication channel. For example, in a TLS connection, you have already agreed on a symmetric key, but you still have to compute the MAC for the individual messages. The signature case finally is useful whenever you want to speak to somebody whom you haven't spoken to yet and whom you haven't got a shared key setup with yet. So for example, whenever you connect to some website with TLS, that website will certify to you with a signature based on a certificate that it's actually the website you're looking for. And you can also use it, for example, to sign document that should later be verifiable by a lot of people. So for example, you put an electronic signature on a PDF document. So these are the different scenarios. There are a few things which overlap. So for example, in the example I had first of a website where you can see the hash value of an image and you get the image from somewhere else, so the distribution image. This is also an application where you can use signatures. So for example, the distributors of your Linux distribution could have a certificate for their public key and could put a signature on the hash value so that you can also cryptographically verify this in case you trust the source of your public key more than the content on the website. Okay, so let's now have a look at the first of these types, namely at hash functions or keyless authentication mechanisms. To remind you of the interface that we have for hash functions, this looks very similar to what we've already discussed for compression functions. Namely, a cryptographic hash function looks as follows. It has an input of arbitrary size, so it accepts an input of arbitrary size, which is denoted here with this asterisk in the exponent of f2. So this reads like f2 are bits and f2 to the star means bit strings of arbitrary length. So this is the accepted input, and as an output it will produce a tag of fixed length t, which is then called a checksum or a fingerprint or a tag, or depending on who you ask. And what the hash function achieves in terms of security property is it transforms the necessity of protecting the integrity of the message M into protecting the tag, which may in some cases be easier. For example, because this tag is a lot smaller or because you can use it as an identifier. So that's the general interface. Now, what is the distinction to compression functions? Because people confuse them quite often. The main difference is that a hash function accepts an arbitrary sized input here, whereas a compression function is a fixed size building block and just accepts a fixed size here at the input. And the trick that a hash function usually does is it iterates a compression function, we will see that in a moment, in order to be able to process arbitrarily long data. Let's have a look at how these should be used. I already explained it in the context of this application example. Namely, whenever Alice and Bob want to use this hash function to protect their authenticity of their messages, then both sides apply the hash function to the message, where Bob receives the message over some untrusted channel where Eve, the adversary, has access. And Alice also sends this tag, but sends it over a secure channel. And Bob recomputes it and compares whether it matches the value that Bob received from the secure channel. That's the general setup. So the idea is that Alice can modify this insecure channel here, but cannot modify this secure channel here. So that's for the functional interface. Now, what about the security notions? There are two types of security notions for hash functions. The first one is very general, but very hard to evaluate. And the second one is very specific, maybe a bit too specific, but it's easier to imagine or to evaluate also for a specific cipher. So let's first have a look at the very general security notion. And this general security notion defines a sort of idealized version of hash functions that we would like to have, which we cannot practically build, but which we would like to have. And this idealized model looks as follows. So it is some sort of machine, namely this random oracle here, which acts as follows. So for every possible input that we can send to it, for every message M, it returns us a uniformly random output string that is specific for this message here, in the sense that if I send in the second message another time, this message a second time, I will receive exactly the same tag. So it's deterministic. However, whenever I give it a fresh message it hasn't seen yet, it will produce a uniformly random tag. And it will then essentially have a list of tags it has already computed. So a list of this message maps to this output. And if I get a new input and I see it already in this list, then I just return the stored value, and otherwise I return a uniformly random value that is freshly generated. Now, unfortunately, in reality, of course, we don't have any magic dwarfs that can do this for us, so we need to instantiate it in some way. And in general, we consider a hash function secure if we cannot distinguish it from, in terms of behavior, from a random oracle like this. In the sense that all we can say about the hash function is, if I give it this message again, it will produce the same output, but I cannot say in advance what the output or the hash value for the next message will be without actually trying it. So I can't predict this in any way, except by trying, which means in the reality computing it. In the idealized world, it means sending it to the oracle. So this is the very vague but very general idea. And if we can't distinguish the hash function from this efficiently, then we consider the hash function secure. More specifically, there are, however, 3 very specific properties that we want the hash function to provide. And these are easier to evaluate than this random oracle notion. And namely, these are the following properties. So 3 classical security properties. The first 2 are properties that are relevant for the receiving end of the hash function. So these are things that a person who has received a tag and maybe the corresponding message shouldn't be able to do. Namely, if Bob has received a tag, it should be infeasible for them to find any message that maps to this tag. And also, if they are given a tag and the corresponding message, they are not supposed to be able to find a second message that maps to this tag. And generically, so if we were dealing with a random oracle, the complexity of these would both be approximately 2 to the power of t trials, where t is the output size of the hash function. Because in order to find a preimage, I can just try random messages until I find one that accidentally matches the correct value. Now, there is also an additional notion which is not so much dealing with the receiving end, but with the sending end. So this essentially protects against a malicious sender. And this is called collision resistance. And it says that for an adversary, it should be infeasible to find any 2 messages such that they produce the same hash value. You will recognize these properties already because we already discussed them for compression functions. And in particular here we have the well-known birthday paradox, which means that finding collisions is generally a lot easier than finding second preimages, for example. And maybe to clarify, in what sense does this protect against a malicious sender? Well, it protects against the scenario where the sender prepares both a nice and an evil message, which are colliding, so they produce the same hash. And this is for a scenario where the message they have first needs to be agreed on by somebody. So for example, this could be an employee at Microsoft, and Microsoft first has to put their stamp on a new code update, for example, after checking the contents. And then the hash value is computed and published. And if the evil software developer in our example is later able to replace the nice and benevolent code by a malicious code which has the same tag, then, for example, Microsoft's hash on it, and thus also Microsoft's signature on it, will still be correct, but the actual content will be something different. And we will later also briefly mention a practical example of where this has happened. Now, writing down these properties is all nice and good. However, there are a few things that you should be aware about, in the sense that it's actually a bit more complicated than it sounds, defining these security notions. So the first 2 points are from a theoretical perspective. Namely, defining the complexity in these cases is actually not so easy, in particular for the case of collisions. Because what does it mean that the complexity of finding collisions is this and this high, when there is no actual challenge that we need to respond now? So we all know that every hash function has some collisions, and once we have found one of them, this is always a valid answer to a collision query, because there is no fresh challenging value. This is unlike in pre-images, where you get an actual challenge, namely a hashtag you have to match. In collisions, you don't get this challenge, and so defining the complexity of the task is a bit difficult, because there is no input to the algorithm that is supposed to find the challenges. No fresh input. There is another issue, namely the question of when exactly we consider a cipher secure, because there are two variants to define this. The first thing we could do is we could say a cipher is secure whenever any of the generic attacks costs more than a specific security level. So for example, any of the attacks is more costly than 2 to the 128 operations. This is one way, which is quite pragmatic, I would say, because this would simply mean that any attack is infeasible. However, classically, we usually require something different. Namely, we require that none of the attacks should be better than the generic attacks. So what this would mean in the hash function case is that for a specific cipher, it's, for example, acceptable if a collision attack costs 2 to the 128, a dedicated one, but it would not be acceptable if a pre-image attack costs only 2 to the 160, because this is less than 2 to the 256, which would correspond to the output size of 256 bits. So if we compare attacks only to the generic attacks, it means that we require that some attacks are more expensive than others. And this is a bit unnatural, I would say. Or it's not entirely clear why we would do that. And there have already been some debates about this, for example, in the standardization of SHA-3, because people couldn't quite agree which on the two to aim for. In practice, there are also a few considerations that are not covered by these complexity things. The first of them is that, of course, it's hard to find pre-images for when the original message was randomly selected. However, if the message we are hashing was not uniformly randomly selected from some space, but has a lower entropy, for example, because there are only a few possible options, then recovering the message from the hash value might actually be quite easy, because we can simply test all possible messages that we would consider applicable in our context and see which one matches. Another issue is that whatever the hash function hashes and authenticates is only a bit string without the specific context or interpretation of this bit string. For example, if I sign a particular version of code, so a particular version, and at a later point I want to replace it with a newer version, the hash of the old one and the signature of the old one is of course still valid, even though I definitely don't want to consider it valid anymore because I want to have it replaced with a newer version. And this happens when, for example, the date or some other context is not taken into account. So if I would program my system to accept all signed code it gets, it would be easy, for example, to push in old versions of software, which could maybe already have security issues that have previously been discovered. Another example for this problem here is when we think of two files which have exactly the same bit string representation, but which we interpret differently. For example, because this particular bit string is both a valid PDF file and a valid zip archive, as an example. So it's a polyglot file. In that case, we also must be sure whenever we hash or sign something to attach a particular meaning or context to it in which it's actually valid, and how it should be interpreted. So how do we now attack such a hash function generically? We already briefly discussed one generic attack, namely simply guessing the corresponding message for a tag, or trying to brute force search for collisions. The simple implementation of this that we've also already seen in the exercises works as follows. So if you want to find a collision, you generate as many candidate messages as you expect to need. Due to the birthday paradox, this is square root of 2 to the t. You write them in a list, and whenever you add, you hash your next candidate, and before you add it to the list, you check whether the item already exists on the list. So whether you already have a collision. And if you find a collision, then you're done. Otherwise, you continue with the next candidate. So this is a valid method. However, it's of course very memory intensive because you need to store all your intermediate results. However, there are algorithms that can solve this problem in approximately the same time with a lot less space, namely with a constant space complexity. So in O of 1 space and approximately the same time as before. And the essential idea of this, I think I've already briefly explained this in information security, is the following. So instead of computing the entire list of candidates and storing all of them, what I do is I start computing somewhere and I recursively compute the next candidate from the current candidate. So I take my candidate message, I hash it, and then I take the hash output as the next candidate message and hash it again. So I don't pick random messages like here, but I compute them recursively. And I always throw away all the previous ones and I only keep the current candidate. And what I construct this way is also called the function graph of the hash function, because I represent all the possible mappings of the function in a graph structure. So what the graph does is it maps one possible input to one possible output. And if I would repeat that for all possible inputs, for example, for all hash input messages of some particular size, then I would describe my entire function in terms of a graph, which always links inputs to outputs. And the interesting thing when I do this is that since there is only a limited number of possible outputs of my function, I know that when I continue long enough, my circle will eventually close. So I will at some point run into a value that I've already seen at a previous time. This is because there's only a finite number of values available. And the goal of these memory-less collision finding algorithms is to detect exactly when this happens. So when exactly I have this meeting point where the tail of my function graph meets the cycle of my function graph. And because of the shape of this thing, of this illustration, this is also called the row method, and it's not only useful for hashing, by the way, but it's also the basis of discrete logarithm search methods, which also work by constructing the function graph and finding something in it. So this sort of discrete logarithm solving algorithms is also called the polar row method. So my goal is, as I said, to find this this nice spot here where the tail meets the circle, because this contains a collision. It contains one point inside and one point outside the cycle, which map to the same value. This is what I want to find. And there are quite a number of algorithms to do this. The certainly most well-known one is the tortoise and hare algorithm, also known as Floyd's algorithm. But there are a number of slightly more efficient ones as well. More efficient because they are slightly faster or because they are better parallelizable. So for example, the van Oorschot-Wiener method is a well-known method that works similarly but is better parallelizable. So how does the Floyd algorithm work? It actually has two separate steps. First, it tries to find out what the length of the cycle is that I have. So if I draw the cycle again here, first it tries to find the length of this thing here, and then it tries to find the length of the prefix. And if it knows both those things, then it can easily find the meeting point here. So how does it go about it? It has two walkers that walk along this graph here. And these two walkers are called the tortoise, which is the slower walker, and the hare, which is the faster walker. And in each iteration, the tortoise makes one step, so it applies the hash function once, and the hare makes 2 steps, so it's faster. And the idea is that both of them walk along this, this graph here, and they do this until at some point they meet again. So this is maybe easier to illustrate by hand than with just one mouse pointer on paper, actually. So the idea is that both of them start walking along in the circle, but not at the same speed. But the one of them is significantly faster. So it has already gone faster along the cycle than the other one. And maybe it has also done already an extra loop in the cycle until at some point the slower of the two has also found the cycle, and the faster of the two has lapped the slower of the two. So it has done at least one more turn than the other one. At that point, they will meet again. It's probably easiest to imagine this situation if you think of something like Formula 1 cars and lapping each other. So überrunden. And once the faster has overlapped the slower of the two, the faster one must have done at least one more traversal of the cycle, possibly several of them. And that means that the distance between the two, so the number of steps that the one has done more than the other, must be a multiple of the cycle length. For simplicity, we will simply assume that the faster of the two has done one more traversal of the cycle, so it has done lambda more steps if lambda is the length of the cycle. Now, how do I find out this distance? Well, that's actually quite easy, because one of the two has done I steps and the other has done 2 I steps. So the distance between the two is exactly I. So my current round counter is exactly the length of the cycle at the moment when the slow and the fast walker meet again. So this way I can find out what the length of the cycle is, or at least a multiple of the length. And now I still need to find out the prefix. But this is actually quite simple, because now I can simply start with 2 walkers of the same speed. I let them, I give the one a head start of 1 cycle length, and then I let them walk. And by the time they meet, one of the two has walked exactly the tail length, and the other one has walked the cycle length plus what's missing, and what's missing is exactly the tail length. So this means that the distance between the two walkers after this second experiment is going to be exactly the tail length. Because when they meet, one of them has walked tail length many steps and one of them cycle length plus tail length many. And this way I've found both the parameters of my system, so both the length of the tail, oops, sorry, that was a bit ugly, so both the length of the tail and the length of the cycle. And when I have both of them, I can simply step forward to this meeting point here. So, oops, to this ugly little meeting point here where I have a collision. And to make a runtime analysis of this is actually a bit more involved, but what the runtime essentially depends on is the expected average length of the cycle and the tail. And by doing quite a bit of complicated analysis, mathematicians have shown that the expected length of the tail as well as the expected length of the cycle is both approximately square root of 2 to the power of t, if 2 to the power of t is the total number of points in my graph. And while I was running this, all I've needed ever to keep ever in memory was my round counter and the two walkers. So this is definitely O of 1 memory. So this means that in approximately the same runtime, namely some constant multiple of square root 2 to the n, I have now found the collision without actually needing all the memory I would have needed for the table. So this means that the generic complexity is not lower in terms of time, but it's lower in terms of data compared to what we've seen before. Now let's have a look at how to build such functions. And there are essentially two useful primitives that we can use for hashing, namely compression functions and permutations. And the easiest way, or the most intuitive way, is probably to take compression functions because they already look like mini-scale hash functions. Mini-scale in the sense that they only take a fixed size input. And so if I want to use one of these compression function designs to build a hash function, all I have to do is I have to start computing at some point, some initial value, for example, 0. And then I keep hashing my message. So I split my message into blocks that are exactly the size that I can fill the input up with. So the size of the message is exactly the difference between the compression function input size and output size. And I always compress in my current message block together with the previous chaining value. Again, here I take the chaining value and compress in the next message and so on. And I continue doing that until at the end, my final chaining value is the hash. Now, this is at least the approximate idea. To actually make it secure as well as applicable to messages which are not a multiple of the block length, I have to do a bit more work. And this extra bit of work is called Merkel-Darmstadt strengthening. So what is the idea of this? The idea is, of course, that I use some sort of padding. So I need to somehow pad my message up to a length that is a multiple of the block size. I can do this by filling it up with a number of zeros and starting with one bit of 1 in order to clarify where the end of the message is. And what Merkel-Darmstadt strengthening also does, mostly for simplifying the security proof of the scheme, is to add the complete, so to add an integer at the end that writes down exactly what the original length of the message was, written as a 64-bit integer. And which padding exactly to use is usually not or is generally not up to the person who uses the hash function, but this is specified as part of the hash function. And this padding must always be applied not only if the message is not exactly a multiple of the block size. And we will see in a moment why adding this length actually makes sense. So let's have a look at the security argument of why having a collision-resistant compression function is guaranteed to lead to a collision-resistant hash function with this construction. And to make this argument, we do a so-called proof by contraposition. So it means to show this implication, P implies Q, we show that if not Q, then not P. So in the present case, this means that we show if the adversary can find a collision for the hash function, then they can also find a collision for the compression function. So this is the contrapositive of the original statement. And to see how this proof works, maybe let's just start working with the assumption that we have here. So let's assume for the beginning that the adversary has found some collision for the hash function, meaning the adversary has found two different messages M and M prime, which are different in at least some of the blocks, but which produce the same identical hash output value. And what we will now do is we will go backwards through the function with our argument and see where exactly this collision has appeared for the first time. So let's start from the back. What we know in the beginning is that the output of the two final compression function calls here is identical. Now, there are essentially two cases of why this can have happened. Let's first have a look at the length of the message. So let's first assume that the two different messages that we had that led to a collision had a different length. So one had a length of L and the other one had a length of L prime. Now, if the two lengths were different, remember that this construction actually writes down the length of the message in the last block. So this means if the length of the two messages was different, then the last block must also have been different because the length is written down inside the last block. So if this would be the case, then we would already have found two inputs to the compression function which are guaranteed to be different, but which lead to the same tag. So this is already a contradiction to our assumption that F is collision resistant, or in other words, it would already, if this is the case, we would already have found a collision for the compression function. So if this was the case, we were successful in the sense of the proof by contraposition. So let's now look at the other case. Let's assume that the length of the two messages was the same, and the content of the two last blocks was also the same. Now it depends on the context of this chaining value here. If these chaining values were different, then we also have found a collision for the last compression function call, whereas if the two chaining values were actually identical, then what this means is that the two inputs to the last compression function calls were identical, but we now can recursively continue the same analysis in the step beforehand. So now we can repeat the same procedure with the second to last blocks. We now again have the situation we have identical outputs, and we can again do a distinction of the cases. Are the two blocks here different? If yes, I have a collision. If not, and I don't have a collision in this part here either, I can again go backwards to the next step. And so on, until I have arrived at the very beginning. Now I can have my cases. Either the message blocks here are different. In this case, I have satisfied what I was looking for, a collision for F. And if they were identical, then it comes back to the initial chaining value. Since we now know that the length of the two messages was the same, we know that for both of them, this initial value here was the same value of 0. Now we have a bit of a conflict, because now we have the situation that either the two message blocks were different, in which case we're done, or they were identical, but in that case, the entire message must have been identical, and the input here was also identical, which is a contradiction to our initial assumption. So this way we have shown that if we assume that the adversary has a hash collision, then either there is at least one compression function for which they've also found a collision, or we have a contradictory situation. So in other words, we have proven exactly this so-called Merkel-Darmstadt theorem, namely if the function f is collision resistant, then the hash function is also collision resistant. So this construction allows to extend the security of the primitive to the security of the entire mode. So that already sounds quite nice, but what could we do better than that? One of the things we could do better is to try to make the thing parallelizable, because the picture we've seen on the previous slide is clearly very serial. So I always have to process all the message blocks so far in order to continue with the next one. There is an alternative construction which is called tree hashing, which is a parallelizable alternative. So the idea of this is to again use a compression function which compresses a bigger input to a smaller output. But now we don't always feed a chaining value and a message block inside, but we have two different types of compression function calls. We have the top layer here, where all the inputs to the entire big state of the compression function is the blocks of the message. These are the leaves of our tree, essentially. And for the lower levels, we always hash two of the outputs of the higher level function calls together and compress them further down. So this way we compress, and so on our data until at the end we only have one final compression value left, and this will serve as our hash value. So this is a potentially very efficient data structure in several scenarios. The first scenario is when I have a lot of computing power in parallel available. Because then I can start computing, for example, the first 3 compression function calls already in the beginning at the same time without waiting for the previous ones to finish. It is also particularly useful in case I have a message which I sometimes modify a bit, and then I need to modify the hash value, but this should come with as little cost as possible. So I don't want to recompute the entire chain of hash values, but only what's necessary. So for example, if I would change, let me see if I can pick a different color here. Let's say, for example, I would change the message block M4. For example, because this is keeping track of some state of my system or so. What would I need to recompute? Well, I can, where am I here? I have to recompute this compression function call. Then this changes, I recompute this call. This changes, I recompute the final call. And that's it. I don't even have to touch all the other ones in case I have stored the intermediate results of there somewhere. So as you know from graph theory or from the data structure and algorithms course, this sort of structure allows to build trees which have a depth that is logarithmic in the number of message blocks that I have. So for example, with a depth of 3, I can hash up to 2 to the power of 3, which is 8 message blocks. And so to update one of these message blocks, I only need to recompute a total of 3 compression function calls in order to update the hash value. But what I need for this is I need to have stored all these intermediate results here that I need together with the updated inputs. So if I have the storage available, then this can be a very efficient data structure. Now I've simplified the whole thing here a bit, because in reality, of course, we need to be a bit more careful. We need, for example, something like the equivalent of a padding rule. So if the number of blocks is not exactly 2 to the power of something, and if the last block is not complete, we need something like a padding rule that works with this. But apart from that, it's a nice building block, and it's also used, for example, in some post-quantum schemes as a building block, as well as a number of more application-oriented systems. There are also some of these hashing style modes defined in very new NIST standards. So this is not just some textbook thing, but there are also standards which specify this kind of tree hash. So these Merkle-Darmstadt constructions that we've discussed so far, they were by far the most prevalent approach for building hash functions for a very long time. So since MD4 and MD5, essentially all the hash functions up to SHA-2 always followed this principle. So the mode of operation was Merkle-Darmstadt, and inside the compression function, we always had a so-called Davis-Meyer construction, which you may remember from the first lectures. It's illustrated here on the right-hand side. Which is essentially a way to build a compression function from a block cipher. And all of these Merkle-Darmstadt ciphers were so-called narrow pipe design. Narrow pipe means that the size of the chaining value here is exactly the same as the final hash size. And this unfortunately comes with a number of downsides. And I want to show some of these downsides in the following, and you will also explore them a bit in the exercises. There is one exception to this statement, namely, there are some variants of SHA-2 which are actually not narrow pipe but so-called wide pipe designs, which means that the intermediate chaining value is bigger than the final hash. So if we look back at the Merkle-Darmstadt picture, after the last hash function call, these wide pipe designs do an additional compression or truncation step where they throw away a bit of the final state and only give out part of the chaining value as a hash value. And this is to defend against some of the attacks that I can briefly show in the following. So the first of these is the so-called length extension property. And this is not a problem of the hash function itself, but it can be a problem when you use the hash function to build something like a MAC. And the property is as follows. So we assume we know the hash of some message M, and we also know how long M is, but we don't know this message. For example, it might be because the message contains a secret key, like for example, a cookie stored in the beginning, or a key because we're using it to construct a MAC. In that case, this Merkle-Darmstadt construction has the unfortunate property that just knowing the hash of a message allows us to compute the hash of extended versions of this message. So where we take the message and add some known value x to the end, and without even knowing the input here, we can still compute the hash of this concatenated value. And this is for the following reason. So if we know the hash of M, then we know this intermediate result here, which we get after applying the compression construction here, to all the blocks of M, including the padded last block. So if we know this output here, we also know the chaining value that would later be used if we appended some other value x to the end here. So instead of recomputing this part, because we don't know M, we can simply start recomputing from here and get the final hash output for an input which we don't even know, because it's secret. And this is a problem if this is used, for example, to build a MAC by putting in the key first and then appending the message, because it would allow us to extend any message that is authenticated this way. So this is one unfortunate property that, for example, the random oracle that we have as an idealized image does not have. So in the random oracle, if we know the hash of a message, then we absolutely cannot predict what the hash of this message plus something is without knowing the message and querying the oracle for it. So it's definitely a property that is not compatible with the security notion of the random oracle. There is another one, and that is that finding second preimages actually can work quite a lot faster than it should for this sort of construction. And in particular, it works faster if the original message that we had to find a second preimage for was very long. Well, very long means, for example, square root of 2 to the t many blocks, or some other very large value. Now here I only want to briefly explain the simplified version of this, but we will work out the full version to the original Merkel-Darmstadt in the exercises. So in the simplified case, where we assume we don't do any padding at the end, finding such second preimages for long messages works as follows. So in the picture here on top, you see the very long message that we are given as a challenge, including its tag t. And what we're supposed to do is we're supposed to find a second preimage for t. Now, if the message is very, very long, what an attacker can do is the following. They can simply try to find a very short second preimage by simply taking random one-block messages and hashing them, and then not trying to directly hit the final hash value, but instead see if they can hit any of the intermediate results here. So instead of drawing it, let me just go to the next slide. Because if the value here matches any of the intermediate results here, then we can extend it to a second preimage by simply taking the message m prime and appending, for example, if the match is here, we can append m3, m4, and so on, up to ml. And this will then be a second preimage for the original long message. So the trick here is that we use the fact that we can find a second preimage not just for one value, but for any of the intermediate values. And if there are very, very many candidates for that, for example, where is my mouse? For example, if the length of the message is 2 to the power of t square root, then due to the birthday paradox, I can actually, after trying only square root of 2 to the t candidates here, expect to find a match with one of these values. Which means that instead of taking 2 to the t like I should for finding a second preimage, I can do it in square root the time if the message is very long, the original one. So this is of course a bit trickier in case the length is included in the final message, because then we need some workaround. But otherwise, this is essentially a consequence of this fact that we have this very small intermediate value here. So this narrow pipe construction. Okay, so these are two unfortunate properties that Merkel-Darmgard has, which makes it a bit less attractive. And in addition to these general properties, there's also the fact that many of the early designs actually had some security flaws. And a very famous example of this is the hash function MD5, where in 2004 and 5, a Chinese team with Xiaoyun Wang and her colleagues found or proposed new cryptanalysis techniques, which were also based on differential cryptanalysis. But they applied it in a very special way to hash function designs by taking advantage of the fact that you can always look inside the hash function. So it's not like in a block cipher where you put some difference in the beginning and then you hope it goes through the entire cipher and you can look at it at the end. But here you can actually work, for example, inside out, or you can try to make some S-box transitions work simply by adapting the message and see what changes. So Wang uses the trick that you can essentially build characteristics and then already satisfy part of these characteristics by modifying the message in small parts. So these are called message modification techniques. And with this trick, she showed that you can actually find collisions for MD5 within minutes if you target collisions for 2-block messages. And she also showed that if you look at the next design, SHA-1, this also should be theoretically possible with fewer operations than the generic complexity. So SHA-1 has a 160-bit output, meaning that it should provide 80-bit security, but Wang showed at the time that with approximately 2 to the 69 calls, similar attacks as for MD5 should also be possible. But at the time, this was too expensive to actually do in practice. It took another 12 years or so until finally in 2017, this was actually demonstrated in practice for SHA-1. And this feat was a bit cheaper in the end than originally expected because there had been some more advances in cryptanalysis. So the final complexity was 2 to the 63, which is still a lot. So it corresponds to about 6,500 CPU years, which were of course conducted in parallel. But they still found the collision, and they also constructed it in a very useful way, so that it was not just a message of random garbage, but it had some actual meaning. So in particular, they created these two PDF documents, which are obviously different and still have the same hash value. And but even before they did that, the previous attacks on MD5 actually had quite a number of implications in practice. This is because, unfortunately, people took a very, very long time to get rid of MD5. So it was still used in many places, and in particular, it was still used in many certificates and browser certificates. And what was already demonstrated earlier on is that it's possible to construct two certificates which look mostly identical, except some small differences in some garbage values. But with one big difference, where one of the two certificates says this certificate is a CA certificate that is allowed to sign further certificates, whereas the other one said, no, this is not allowed. And usually if you go to a CA and want a certificate for your website, you only get this type. You only get certificates that are only valid for your website and that cannot spawn any further certificates. But if you build two certificates which have a colliding hash value, and one of them allows you this and the other one does not, and you go to a CA and get the one signed, then the signature will also be valid for the other certificate, which would then give you extra powers, such as the ability to sign other certificates. This is called a rogue CA certificate because it allows the attacker who created the collision to essentially sign whatever they like, and it will be accepted by major browser vendors, for example. And while this was originally done in an academic paper, it later also turned out that this was actually used inside some malware, namely the Flame malware. This worked because the code signing was tricked with this sort of MD5 collision. So these sort of attacks actually had some real financial ramifications for some people, because this Flame malware was used to attack, for example, relevant infrastructure and things like power plants. Okay, so all of these things sort of showed that the Merkel-Darmstadt monoculture that had been prevalent until this time was a bit of a problem. And so people started looking for alternatives in the context of the SHA-3 competition. So a cryptographic competition to look for a follow-up design to replace SHA-1 and MD5, and to also serve as a backup in case SHA-2 showed similar problems. So to date, SHA-2 still looks absolutely secure and looks to have a very good security margin. But at the time, people were really a bit unsure because there had been so many attacks on similar, slightly weaker designs. So they wanted to have a replacement ready in case there were some threats for SHA-2. So one of the requirements of the competition was also that the new design should look as different as possible from the SHA versions, to prevent any of these type of attacks to carry over to the new replacement scheme. So this competition ran from 2008 and had quite a number of submissions in the first round, a total of 64. And of those, 5 were after a while chosen as finalists. One of them co-designed by some former colleagues from TU Graz here. And in the end, the winning design was the Ketchak and now SHA-3 that you probably already know, which shared a designer with the AES scheme, and he designed this together with his colleagues. So what are the advantages of this new hash design compared to the previous stuff? First, from a purely aesthetic perspective, it's a really elegant and innovative design. So it looks completely different than the previous ones. It uses permutations instead of compression functions, and it also has a very different construction of the primitive inside. It's also more efficient than SHA-2 on many platforms. In particular, it's a lot easier to implement in hardware, for example. And it's also quite flexible. So NIST actually decided to not just standardize the original hash function design, but to also suggest several related designs, which expand the functionality a bit. So one of the things they designed is Shake, which is not a hash function, but something similar. It's a so-called extendable output function, or XOF. What this is essentially a hash function, but it's able to produce arbitrarily long output. So the hashtag doesn't end after 256 bits, but you can get as much output as you like. This in particular means that this looks something like a random number generator, because you can put in some data and then get out arbitrarily long amounts of output data, which you derive from this initial seed. There is also a related MAC construction, Ketchak MAC, which is very, very simple to construct from the hash function, as well as some variants, in particular a parallelized variant that is supposed to have a similar purpose as the tree hash that we saw earlier. And in case of Ketchak, this is called parallel hash. So what does the simple hash function look like? It works again by splitting the message into blocks, but instead of putting them into compression function, the message is XORed to a part of the chaining value. So in contrast to the previous case, we now have a very, very large chaining value that has two sections, the so-called outer part here, which interacts with the inputs and outputs, and the inner part, which remains unchanged between the steps. So in every step, we XOR, while we are absorbing data, we're XORing the data blocks to this outer part, and then apply the permutation. So you can also see this as a compression function, as if you like, because you do compress in the message into this intermediate state, but it does not actually satisfy the requirements of Merkle-Darmstadt, because this is not a collision-resistant compression function. It is, however, still a secure construction. So what it does after absorbing all the stuff is we can switch phases to a squeezing phase, and now we can extract as much of it as we want. And this again works by letting the outer part interact. So to get some output from the thing, I simply copy the outer part of the chaining value, but I do not give out this inner part here. So there is always this secure inner part, the size of which is called the capacity, which is very essential for several security properties. And you can already see here that you can, of course, continue this as long as you want, and can very easily extend this to an extendable output function. And you can also imagine that this is relatively easy to transform into a MAC, because you can simply add the key as the first block here, and then the rest of the computation stays the same. This way you could also produce, for example, a MAC with a longer output. So it's a very flexible construction. And one of the big differences compared to SHA-2 is that this state here, this chaining value, is really, really large. So this is 1,600 bits large in the case of Ketchak. And only a part of this is allowed to interact with the outside, whereas the rest always remains secure inside. So in particular, you also never give the full output to the adversary at the end, and this means you cannot do something like message extension. Of course, we also need a padding rule here, but this can be a bit simpler than for Merkle-Darmstadt. So for the sponge, or for Ketchak specifically, the padding is simply we append a 1 bit and as many zeros as we need. In the case of Ketchak, there's also one initial thing we need to XOR, namely, oops, here I am. We need to XOR an additional 1 at the end. This is supposed to show how big the rate, so the outer part of the state is, because this will be in the least significant bit of the of this outer part. So the first one marks where the message ends, and the second one marks the size of the blocks in order to distinguish different variants of the cipher. And this inner part that I talked about is never under the attacker's control, so the attacker can neither manipulate it by XORing stuff, nor learn it in the squeezing part. And this prevents all the nasty properties that we saw with Merkle-Darmstadt earlier. And it also means, so it also defines the security level of the construction, because what an attacker can always do to find a collision is they can try to construct a collision in this inner part, because if there are differences in the outer part, they can always override that with an XOR. But in the inner part, they really must hope for a collision to happen by accident, like in Merkle-Darmstadt. So if this inner part is large enough, at least twice the security level, then finding such a collision is feasible. And this is also where some of the discussion related to security notions that I mentioned earlier arose, because I mentioned earlier the question whether we should aim for a particular fixed security level, like 128 bits, or whether we should aim for a security as good as generic. And this is relevant here because if I find such an inner collision in the inner part of the sponge, I can not only construct a collision for the final hash function, but I can also build second pre-images with the same complexity. So in order to make second pre-images as hard as they should be generically, I would have to make the inner part not twice the security level, but 4 times the security level. Because second pre-images in this view should be twice as hard as collisions. Now, this is maybe a bit unnecessarily inefficient or unnecessarily generous. So NIST considered not doing this and instead just doubling the security level to get the size of the inner part. But that would mean that second pre-images can be found with the same complexity as collisions. And some people in the crypto community were very skeptical about this and found that it doesn't match what they usually expect as a security notion. So in the end, NIST actually standardized both variants. The standard Ketchak is the generous thing which has 4 times the security level inside. But there is this Shake version which can produce the arbitrarily long output. And Shake also takes the more efficient choice and just doubles the security level to get the size of the state. Okay, so which of these functions should you now use today and which ones not? Well, MD5 and SHA-1 are definitely broken. SHA-1 is still secure, though it is not necessarily supported in the newest TLS versions. So this SHA-1 comes with one small variant which has just 112-bit security, and this was not accepted in TLS version 1.3. So they only accepted things with a security of 128 bits or more. Unfortunately, SHA-3 Ketchak has not yet made it into the standard. This is because it's too new still. But I hope it will be supported in the future because it's a very, very nice design and has quite a number of advantages compared to SHA-2. That concludes the stuff I wanted to say about hash functions. So now let's have a look a bit at message authentication codes. So how can we add a key to this whole construction? The interface is otherwise quite similar as for hash functions. So we also have an arbitrary size input message and a fixed size tag, but the MAC additionally accepts a fixed size key as an additional input. And this is an important difference because what MACs do is they transform the challenge of protecting the message into the challenge of protecting the key. You might remember this is different from the hash case where the task was transformed to protecting the output. Now it is transformed to protecting the security of the key. So both the message and the tag can be transmitted over an insecure channel. The thing that has to be kept secure is the key. Otherwise, you can work with it quite similar as for hash functions. The only difference is that you now have the keys you need to protect and that you can now send the entire stuff, including the tag, over an insecure channel. What security notions do we have for this type of scheme? The main security notion is called SUF-CMA, or in long, strong unforgeability under chosen message attacks. So SUF is for strong unforgeability and CMA is for chosen message attacks. What does this translate to in plain sentences? It means that if an attacker can query any tags for messages of their choice, it should still be infeasible for them to produce any new and valid combinations of a message and a tag. So in other words, even if they are so strong that they can trigger an oracle to encrypt any message that they want, they cannot use this information to produce any forgery of their own. So any combination of message and tag that was not produced by the oracle and still verifies successfully. Which generic attacks are there based on this interface against this notion? Now we have two of them, and we have two relevant parameter sizes. The first of them is that we can try to guess the correct key. If the key is k bits long, we have approximately 2 to the k trials before we hit the correct one. And this is also called offline trials. Why? Because these are computations I can do myself without knowing the correct key. I just need one correct input-output pair, and I can try it on my own. There is a second type of attack, namely guessing the key, the tag for a particular message. So here I don't even try to find out what the key is. I simply try to guess, if this is the message, what could be the correct tag. And this is, if the tag is t bits long, then this is successful with probability of 2 to the minus t. So after approximately 2 to the t attempts, I probably have a successful hit. Now this is a so-called online trial, because you actually need to ask the owner of the secret key whether your key is correct. So you must be in connection with an oracle to do this guessing. There is a closely related concept to MECs, which is phrased a bit differently, and this is called pseudo-random function families. The difference would be that the security notion for PRFs is that they should produce random-looking tags. So it should not be possible to tell the tags apart from random strings or to predict them in any way. The reason why we can talk about MECs so quickly at the very end is because we can easily build them from building blocks we already have. For example, if we already have a hash function, what we can try and do is to push the key together with the message into the hash function somehow. For example, we could try and define the MEC under key k of a message m as follows. We could simply take the key, append the message, and then put that into the hash function. This is called a secret prefix MEC because the key is the prefix to the message. Now this is problematic if our hash function happens to be a Merkle-Darmstadt construction because of the length extension property we discussed earlier. In sponges we don't have this problem, which is why, for example, the KMEC MEC function based on Ketchak uses exactly this construction together with the shake hash function. Of course, instead of appending it in the beginning, we can also append it at the end. This is then called secret postfix. This is also okay, but it relies on the collision resistance of the hash function. So on the one hand, the nice thing about this is that if we take any hash function, for example, a Merkle-Darmstadt hash function, and construct this, it is probably okay. However, we have the problem that most of the computation, namely everything that depends on the message, is actually under the attacker's control. And they know exactly what they're working with because the key has not yet been used at that time. So they can try things like finding collisions. Whereas in the prefix case, starting from the very first block, we already have a secret input, meaning starting from there, the attacker has absolutely no idea what's going on inside the cipher. So in particular, they cannot easily try to build things like collisions, which is the reason why these secret prefix MECs could potentially be made more efficient, because we don't have to be careful of collisions so much. We can also, of course, just do both. This is called a sandwich MEC. and is also used in a very popular MAC construction, namely the H MAC, where H is for hash-based. And this H MAC construction is, in my opinion, a bit ugly, because what it does is it actually calls the hash function twice. But in the end, if you draw a picture of it, of what's going on and what's happening, it is essentially a sandwich MAC or a sandwich construction. So what HMAC does is it takes the message and prepends it to the message, like in a secret prefix, puts that into a hash function, but then at the end concatenates this result with the key again and puts it into the hash function again to actually get the tag. So this is supposed to be a sort of fix for this length extension problem. But overall, it's a bit ugly because it has some artifacts based on the way it's constructed. For example, you have these arbitrary constants that you're supposed to XOR to the keys in order to have two different keys that you're using, which is a bit of a relic from the provable security construction that this has. So overall, I think it's not very elegant, and it's also not as efficient as it could be, because something like a secret prefix MAC can be made more efficient. What we can also do instead of using an unkeyed scheme and keying it is we can take a keyed primitive from the start. And one of the examples of how you can do this, quite an intuitive example, is the so-called CBC MAC. So you might remember the CBC construction for block ciphers. This was an encryption construction, and CBC is short for cipher blockchain. In the MAC case, this is actually really simple. You simply chop your message into blocks and XOR the message to the current chaining value, put it into the cipher, XOR the next message block, put it into a cipher, XOR the next message block, and so on, and you give out the result. So that's the plain construction, the pure CBC MAC. Unfortunately, this pure construction has some security problems. And you can find these problems if you think at what happens if you, as an adversary, you first request the tag for a one block message. So in this picture, this would mean if you have a message that ends here, then the tag of the message is simply the output of the block cipher here. Now you could use this intermediate result to forge the tag for a different message. How can you do this? You can try to add something, so to concatenate something to the message, which overall again leads to the same tag T. So if this intermediate value here is called T, you can try to choose M in such a way that the output here is again T. And how would you do that? Well, there is one input to the block cipher of which you already know the output, and this one input is M1. So if you choose M2 in such a way that the input to the block cipher is again M1, then you will again get the tag T. So in particular, if you choose M as T X or M1, then what you get is you have T plus M1 here, you add T, so T cancels out, and all that will remain is M1 going into the block cipher again, and the tag will stay the same. So this simple construction has a security flaw. However, there is a relatively simple fix for that, namely by adding another key before the very last block cipher call. This is again not very elegant, but it does work. And this modified version is called CMAC. You will notice that almost all MAC schemes have a very similar name, some letter that describes some property of the MAC, and then MAC. So there is CMAC, KMAC, HMAC, and actually somebody once tried to collect all the MACs there are and was able to find a MAC for almost any letter of the alphabet published somewhere. So MAC naming is a very boring affair. There is also one other construction which has the same name format, namely GMAC, where the G is short for Galois, a mathematician that we will meet again very soon. And one of the main goals of this MAC is to build a construction that does not need a call to a cryptographic primitive for every message block. So far we always needed at least one compression function call or one block cipher call for every message block. And this construction here does without that. It works as follows. So it does use a block cipher call, but only at the very beginning here. So at the beginning, it encrypts the value 0 one time to produce some helper key L here. And then this looks a bit similar to the CMAC construction. The message blocks are always XORed to the current chaining value, but instead of putting a block cipher here, the intermediate value is simply multiplied with the secret value L before the next block is XORed, and so on. So this is a bit like a CBC construction, but replacing the block cipher with a simple multiplication. And this is nice because the multiplication is usually more efficient. There is one issue with this, namely, this is a sort of one-time MAC. So as soon as you use this construction twice, you have a problem. And for this reason, unusually for a MAC, this MAC actually requires a nonce as an input. So it requires this one-time value here, and the final result of our chaining needs to be XORed to the encrypted nonce before it's output as a tag. And this nonce must never be reused, otherwise this intermediate key here, this authentication key L, is leaked, so the adversary can recover it. And this particular MAC construction is part of an authenticated encryption scheme called AES-GCM that you have possibly already heard about, because this is the default scheme we see, for example, in TLS as well as in many other protocols. Because it's pretty efficient, and as long as you don't do nonce misuse, it also has a good security. But the nonce misuse thing is, of course, a bit of a problem. If repeating the nonce just once allows you to recover the intermediate key, this is really a nasty property. Okay, so to conclude, what did we hear about today? We looked at constructions for schemes based on a primitive, the ingredient, plus a mode of operation, the recipe. And we looked at two schemes that we built, namely hash functions and message authentication codes, which are for unkeyed and keyed authentication. And we saw that for hash functions, there are two popular constructions based on compression functions like in SHA-2 or based on permutations like in SHA-3. And for MACs, we very briefly looked at 4 different MACs, each based on one letter of the alphabet plus MAC. And the one letter gives you a reminder of what's inside. So there's HMAC with hash functions inside. There's KMAC with the Kerchak permutation inside. CMAC with a block cipher inside, or GMAC with a Galois field multiplication, which we'll talk about in one of the next lectures as its internal building block. Okay, I think that's it. Yeah, now we have time for some questions if we have any, or if you have any. Otherwise, thanks a lot for listening and enjoy your weekend despite the corona situation, I hope. Let's see whether we will meet again here in the streaming office next week. I think I might actually be streaming from my home office next week. If this is the case, then I would also be curious for your feedback regarding the choice of tool for the exercises. So if I do move to the home office for next week, then I would switch to a YouTube stream for the lecture. And for the exercises, we can either stay on Microsoft Teams or also switch to Discord. like the other group. If you have any preferences on that, in particular in light of the issues that we had today with Teams, I'd be very happy for your inputs on that. So in the meantime, goodbye YouTube. Let's end the stream there.